All right, so we're going to start chapter 5. We're going to start chapter 5 with the concept of work and energy. Now, think about it logically, right? To move anywhere, to get an object to just move laterally, vertically anyway, it takes energy. It takes energy. Now, you yourself are doing work to that object. So by me taking this laminated sheet of paper, whatever you say, pushing it, it takes a certain amount of work to do that. And what I'm doing is I'm changing the amount of energy of the object. The energy of it could be a function of many things. It's height, and we'll call that potential in this chapter. It's speed, which creates kinetic energy. If it has energy stored in it, like think about something like a spring. When a spring is compressed, and then you click a button and it shoots an object or releases it, that's stored energy. So there's lots of types of energy. There's internal energy, chemical energy. So what we're going to look at in this chapter is specifically work and energy and how those two things are really related to one another.
So when we're determining the work, right? Are we given both the variables to find it, or do we have to find those variables at some point with what it is?
One or the other, either one. Yeah, either instance. Yeah.
I was kind of like watching videos on YouTube and stuff. Why is like the regular version of work so different from the physics version? Like why is like
What do you mean?
like
The physics version of work, let me explain that first, then maybe it'll clear it. The physics version of work, which is what we're going to start with, we can even just go to the next slide to show you what we're going to do. The idea that you apply a force over a given distance. A force over a distance. And think about it logically, right? If I apply a force on this and nothing's happening, I'm not really doing anything to this. I'm not doing any work on the object. But if it starts to move, then I am causing its energy level to change, so I'm doing work on it. Work is a measurement, really, or it's like a balance between the amount of energy an object has and can gain or lose. So if you think about this, right, I take a garbage can, right, I slide it across the floor. Why does it stop? It stops by friction, right? Well, the floor is doing work on the garbage can. It's doing work in the sense that it's providing some sort of resistive force over a distance. The frictional force acted on this garbage can for a distance of 5 meters, or 4 meters, whatever the heck it was. So as a result, the energy in the garbage can decreased because it lost energy to friction. So as a result now, it stopped moving, it has no energy when it stopped moving. When it was moving, it had energy, but work is something that causes an increase or decrease in the object's energy.
so let's say I'm like holding up like a really heavy textbook like this, but my arm's not moving and neither is the textbook. Technically I'm not doing any
No,
work.
you're not doing any work there.
Right.
It's odd to think about, right? Yeah. So, that's a really good point, because if you hold an object, literally just hold it there, you're not doing any work. But if you lifted the object from here up to here, you're increasing the object's potential energy, and thus doing work on the
What
object.
if you're dropping?
It's decreasing the object's potential energy. So gravity is doing work on it.
So then the work is negative, or the work?
Yeah, we'll talk about negative and positive work also. It can have vectors.
And then another thing is so then we've already gone over this a lot, but so then you were talking about how friction stops the garbage can, right?
Mm-hmm.
There's no gravity, there's no friction, there's no external forces.
There's no work.
It's no work. So it just moves.
Yeah, it's like when Zoe kicked the object in space, right? There's no friction result, no friction preventing its motion, no gravity pulling it down or anything like that. So
It keeps on going forever.
yeah, now keeping in mind though, for that instant that Zoe applied a force on it, for that small distance before she let go, she did work on the object, which increased its energy level, but because there's no external forces, there's nothing to decrease the energy level to get it to stop moving. She's increased its kinetic energy as a result by hitting it, but there's nothing to stop it or to slow it down. When you drop an object, gravity is doing work on the object. Gravity is doing work. The force, the weight of the object over that given distance is how much work will be done on the actual object. So in this chapter, we're going to use this formula. Force times distance times the cosine of theta. Now, it's important to notice that theta, write this down please, theta is the angle between the force and the displacement. Theta is the angle between the force and the displacement. So for example, let's go back to the sled. even if it's being pulled at an angle. Let's say that the object is moving this way. It's moving horizontally. It's being pulled at an angle theta. Well, what we'll notice here is that theta is this angle in this problem. Now, what if you were pulling this object at that angle, but somehow it was moving vertically instead? Instead of moving horizontally, it was moving vertically. Well, now theta is this angle in this process. So it depends on the direction of motion and the actual force applied. That's where theta will always come into play. You won't have to use sine. You could always use cosine in this chapter, as long as theta is the angle between the direction of motion and the force applied. Okay, direction, motion, and force applied.
So there's no angle involved, and it's just
What would theta be?
equals what?
What would theta be if there's no angle involved?
Just zero? So
Yeah.
it would just be
What's the cosine of 0? Anybody know?
0.
It's 1, believe it or not. You'll learn about this in your trig class this year. Okay, you'll get into more with the trig with cosine and sine, but the cosine of 0 happens to be 1. So if you apply a force at no angle at all, so you apply a force horizontally, this goes to 1. It kind of just drops off.
So then it's basically just, so if there's no angle involved, which some of the problems were like for
It's just
pi,
force times distance.
It's just work equals force times distance.
Yep, it's one of the simplest formulas you'll learn. Okay, that's when theta equals 0. Now, we'll talk more in the next example, and you'll see how you can get negative work. All right, so let's look at the first example here. Oh, but no, sorry, units. Joules, capital J. Okay, a joule is represented by a Newton times a meter. How do we know it's a Newton times a meter? How do we know a joule is a Newton times a meter? Because it's very good, Ellie. It's obvious, and Ellie saw it. Force times distance. Force is measured in newtons. Distance is measured in meters. If work is force times distance, then it's Newton times meter. A Newton times a meter is a joule. Joule. Okay? Please don't write Jewel. When I see that, I saw that on a few tests last year. I'm like, have you been awake this whole chapter? Okay, it's not jewels, like jewels that you would buy, like jewelry and stuff. Okay? I mean, like in class or not? So, what we're going to look at is an example here of a basic one first, and then we'll go into one that has an idea of negative and positive work and how they can be different. So this says how much work is done on a shopping cart when pulled 12 meters by a force of 75 newtons at an angle of 60 degrees. Now, you need to use common sense. Which way does a shopping cart move, horizontally or vertically? I hope you're kidding. A shopping cart most definitely only moves, okay? It only moves horizontally. So the motion is this way. Now, it moves 12 meters, and the force applied is 75 newtons. Oh, that's not the right location for that. Hold on. Why did I put that in the wrong spot? Where should it be? Where should the force really be? What? Like that? That works also, actually. That's true. I didn't think about it. It says pulled, though, for now. But what it... You never pulled a shopping cart before?
No.
Instead of pushing? Why would you grab the front of it and just pull behind you?
I mean, like a boat. Well, sometimes you read it.
No, we can say push. We can say push. Push works also, though. Either way works.
When I stand on the back, like,
Yeah, so we could do this. We could say it's pushed like that instead, right? That works too. So we'll call this angle 60 degrees. Okay, or you could have said it's pulled like this, and this angle would be 60. Either way works. We'll say push, because I guess you're right. You do push it. I mean, if you go to like Costco, you ever like pull on the, instead of pushing, they're like the flatbed ones? Yeah, that's what I was thinking of. You know, like a shopping cart where you pull behind you. So let's say you push it, right? Okay, pushing works.
Not a lot of people pull shopping carts.
So-
I feel like it's mostly pulls.
Thank you. Your direction of, I'm glad we have that analysis. Your direction of motion is horizontal. Now this is where it's going to get a little bit tricky. The angle theta is always between the motion and the force. Well, here's the force right here. How do I know 60 is there? Because, ready? If it's moving horizontally at this point, the top is also moving horizontally. The bottom is also moving horizontally. So technically the direction of motion could be drawn up here at the top. Okay, so I could draw the direction of motion up here at the top and show that this is the direction of motion. This is the applied force. So here's your angle theta. Okay, there's your angle theta. Remember, if the top of the card is moving horizontally, so is the bottom, so is the middle, because it's one object, okay? It's one object. If you were to take your bag and just pull it slightly across the table like this is the same example. The top is moving horizontally, so is the bottom. So whether you draw your vector of displacement from the top as that blue line or the bottom, it really has no change in this kind of a problem. So our angle is 60 degrees. The work done is force times distance. It's d, notice, it's not displacement, but it's distance here, times the cosine of theta. The force is 75 newtons. The distance covered is 12 meters. And the angle is 60 degrees. So how much work is done on the shopping cart by the person? How much work is done? Make sure you're in what kind of mode? Degree mode, please. Degree mode. When? 450. When was it? What kind of calculator? I'll look for it. Like this one right here?
Yeah, it was black.
Like that? Found one. Those are
And it's
the best.
broken.
It's in my office right now.
You guys get
I was just waiting for somebody to come for it. I don't like to be like, anybody lose calculators? And it's like, who knows if they did.
Oh, cool.
Yeah, it was like 2 or 3 days ago probably.
Yeah.
It's on my desk right now actually. Okay, so 450 joules. Now, let's talk about what the significance of this means. Let's talk about the significance of this. The person did work on the shopping cart. So they caused the shopping cart's energy to increase. So you have what kind of a sign here? A positive sign. Notice this is a positive amount of work done because you're increasing the energy level of the shopping cart. You're making the shopping cart go faster. And we're going to see in the next section when we talk about kinetic energy how we can actually determine the velocity of the shopping cart using energy. Instead of using kinematics with displacement and acceleration, all the stuff we've done to find velocity, we can find velocity using energy methods also. And we're going to talk about what's called the work kinetic energy theorem that relates work and kinetic energy. Okay, we're going to see that in the next section or so. Anything else I want to mention for this problem? No. Let's go to the next one. The problem says the following. What would the angle theta be if the force is a horizontal force in the direction of the displacement? And we already talked about this, Ben already alluded to it. And what would it be if the force is in the opposite direction of displacement? So let's take a look at an example of what we're talking about here. So we've got an object. Let's draw a free body diagram real quick. We've got an object. We're told that, and we know that, gravity pulls down. Normal force pushes up. And we're told that the force is a horizontal force in the direction of the displacement. So let's say that it's going to the right. Let's say that the displacement is to the right. That's the motion of the object. So if that's true, that means that the force, it says, is in the direction of displacement. So let's put a force this way. I'll call it FP because it's a push or a pull or some sort. And it's in the direction of motion. So Ben already asked this question, so we kind of already discussed it, but let's prove that it's true. So think about this, and I'm going to use a little line feature here. Okay, so I know, this is wild. So let's say this is the displacement right here, right? Technically speaking, we talked about this earlier, the bottom of the object moves that way, the top of the object moves that way, right? Every part of the object moves horizontally. So if I look at this, and I put the displacement right on top of the applied force, what's the angle between them? What would the angle be?
0.
Just 0 degrees. If I had this line, or if I knew that the object was moving, let's say this way, well then there would be an angle there, right? There's the angle that you would see. But it's not. That's not the case. Okay, the case at hand is that this is the direction of motion. So if I have the direction of motion as the bottom, I can translate this direction. You can translate it up and see that the angle is definitely 0. Now, if I look at the second case, where the force applied is in the opposite the direction of displacement. So now let's take a look at this. Can I do an arrow actually? Is there an arrow feature? There is. Nice. I want a really skinny arrow. There we go. Okay. So let's say the direction of displacement is this way now. Well, if that's the case, then the force applied should be to the left instead, because it's opposite the motion. So we would say that the force applied would be this way. Now, it can't be a pull to the left and move to the right, so what would this force be? What force acts against motion?
Push.
Not a push. What acts against motion? What stops something from moving? Friction. So this would be FF. So FP might still be there. You might be pulling still to the right, but FF pulls back. What's the angle between FF and the red directional? That red arrow and FF. What's the angle between them?
180.
180. Think about that. It's a straight angle. Remember you learned in geometry last year about your angles? So this angle from here to here is 180 degrees. If you have a vertex here and one vector that way and the other vector that way, this angle is 180 degrees. It's called a straight angle or a straight line, really. So what you'll recognize here is that friction acts opposite motion always. Always, always, always. So the angle you're going to always use when calculating the work done by friction will always be 180 degrees. Again, theta, you can write this down if you want. Theta for your frictional force will always be 180 degrees. So if you're trying to find the work done by friction, you're going to have F times D times the cosine of 180. Go ahead and calculate it. Type in cosine 180. And what is it, Ellie?
-1.
It's -1. So what does that mean? What does that mean?
Could be a negative work.
Yeah, because what's happening? What does friction do? It decreases the amount of energy an object has. Let's write this down. Let's write this mathematically. All right, there's our formula. Whenever it's friction, we'll call it FF if we want. If you want to know how much work friction does, you take the force of friction, right, times the distance that friction acts on the object, times the cosine of 180, because friction acts opposite the motion. Well, cosine 180 will always be -1. So the amount of work done by friction is always going to be negative FF times D. This is really -1, so I can get rid of it and replace it by just putting a negative sign here in the front. So the work done by friction could always be calculated by negative FF times D. Okay, that's why friction reduces an object's motion, because it decreases the amount of energy. It takes energy away. I'm running, right? And I've got all this energy because I'm running. And what's stopping me? The wind is pushing back against me. It's resisting my motion. It's decreasing the amount of energy I have. That's literally what happens here. Ready? I push the object. As soon as I release it, it's got a lot of energy because it's moving. Right? It's moving. But it eventually stops. Because from here to here, where I stop moving, it's a certain distance, that's D. A force of friction was applied to the, a force of friction was applied to the bottom of the trash can, that's FF. It's negative because it loses energy. Okay? The energy of this object is decreasing, which is what causes it to come to rest. And think logically, right? When something is moving, it has energy. When it's not, it doesn't. Think about when you're laying on the couch and you're tired after a long day of school and all that work. You have no energy left, right? You're like, oh, I'm so tired. You're probably not moving. The idea makes sense. If you're moving, don't you have a lot of energy? If you're working out, you're playing sports, don't you have a lot of energy? Motion and energy are synonymous in a sense. The more motion, the more energy. So as the motion decreases, the object is losing energy. It's losing energy due to friction. Right.
Why didn't you cross out the cosine 180?
I didn't cross it out. I just said, like, this goes to -1. So I could simply just put a negative in front, because -1 times this formula gives me this down here.
Oh, okay.
Okay? It's like, if it were like... What's that
Sorry,
funny?
I understood.
No, it's good that you asked that question, because if you don't know what you're doing with this, why is it negative? The -1 has to come in front here. We're going to see in a moment what happens if it's cosine of 90. What's cosine of 90?
Oh, I'm going to look it up.
Go, there you go.
Cosine 90, enter. No, just kidding.
I mentioned 1. 0.
What is it?
0.
Zero. Well, let's talk about that in a little while. We'll see where we allude to that idea. So the angle has a big, important role on this. Okay?
Oh, is it because it goes straight up?
Yeah, it'd be like applying a force this way, yet it moves up. you're not causing it to move up if you apply a force this way, right? So you're not really doing work on the object, so your work done would be 0 in the end. Okay, yeah, good. Here's a diagram of this. We can see exactly what we were just saying. If you're applying a force to the right and it moves to the right, you have positive work. If you're applying a force to the right and it moves to the right, you have positive work. But if you're applying a force to the left and it moves to the right somehow, you have negative work. You're doing negative work, and think about that for a second. Okay? These are like these little spring-loaded cars, right? These little spring-loaded cars. If it's coming towards you, right? So you're playing with your younger brother or sister or cousin. They're like 2 years old, so they love these things. You pull back, right? And you let go, and what happens? It starts to move on its own because you're storing energy. That's internal energy in the spring mechanism. So when you release it, it's got all this energy and it's moving towards you. But if it's about to hit you, you might put your hand out and stop it, right? So what you're doing is you're applying a force that way, and it was moving this way, right? So you're doing negative work, causing it to decrease in energy, and as a result, the object doesn't anymore move, it stops. So this is an example of negative work. Better than not.
So work isn't really the amount of force or the amount of work that you really put in. It's the amount of work that your body exerts onto the object, in a sense. Of what manipulation you can do. Still, like if you're slowing something down, right? I'm not like, I don't get less tired. I don't have put in less work. You know, I'm not like, oh, this is like so much easier or whatever, easier than not doing anything, right? Because in theory, something that would be negative, if I was slowing something down, the work would be negative. Like it would make me just feel like it was easier than not doing something. So in theory, it's kind of what you exert on the object of what your body exerts on the object.
It's all about what you said at the end there, on the object. Work is always done on an object. And that's the key. Think about what causes the change in the object's motion and what provides that. So friction works on the object. Your push works on the object. It has to be something that affects its motion, which is why the formula is force times distance, really. Honor?
I'm confused with like negative work. Like, do you put in negative work or does the object?
You do negative work on the object, which causes the object's energy to decrease. When you do negative work, it lowers the energy of an object. When you do positive work, it increases the energy of the object.
So like stopping something
Is negative work because you're lowering its kinetic energy. Lifting this object from here to here is positive work because I'm increasing its potential energy.
So what if you lower it down?
If you let this go and drop it, right, it falls to the ground, technically, that's a little interesting there actually, because you're doing, gravity is doing negative work on the potential energy, it's lowering the potential energy, but it's increasing the kinetic energy. So that's a little bit trickier. And we'll get to that when we look at energy balance. Okay? Okay? Little bit of last chapter work with this, okay? So you should also know in this chapter your formula like force of friction equals mu Fn, that's going to come up because work is done by friction a lot. So you're going to use Ff equals mu Fn a good amount. And?
On this, doesn't mean to say a student pushes a 20 kilogram?
No, I'm giving you the weight of the object. I'll give you the weight of an object.
Weight in newtons?
Fg is measured in?
Oh, newtons.
Yeah, there you go. It's like pounds, right? A 20-pound desk. So I'm giving you the weight of the object. Okay? You're given the weight of the object. You're not given the mass this time. So a student pushes on a 20-newton desk with a horizontal force of 12 newtons, a distance of 24 meters. Assume the coefficient of kinetic friction between the desk and the floor is 0.2. Okay, 0.2. That's our mu value. Mu is 0.2. How much work is done by the student on the desk? How much work is done by the floor on the desk? What is the net work done? So what are we going to have? The work that the student does, what kind of work? If you're pushing it to make it go faster, what kind of work?
Positive.
Positive. The floor is doing what?
Negative.
Negative. So what are we going to try and do again?
Add them.
Yes, exactly right. To find the net work. Just like we're trying to find net force, we take our positive forces and subtract the ones in the other direction to get the net force. Same thing with net work. So let's start with part A. Part A. How much work is done by the student? So what's the student's force on this object?
12.
Good. The weight of the object? What's the weight of the object?
20.
So what's the normal force as a result? It's not moving vertically, guys. Nothing about vertical motion, right?
So 0.
20 also?
Wait, I'm confused. Oh, because it's like,
Remember, it's a state of, remember, like you did this on your last test. If it's not moving vertically, normal force and Fg are always going to be balanced. If there's no angular component of your force, normal force and Fg are always going to be out of balance. If I were pulling at an angle, Fn would not be 20, and that's important to know. Okay, so this is in this case. What's acting against the motion?
friction.
No,
No?
no, yeah, you're good. I was just writing for you. And friction's force is what? Doesn't say, right? Oh, obviously doesn't say. We know the mu value, we don't know friction. Okay? And please be careful, FF is not 0.2, mu is 0.2. Some of you in your test wrote FF equals and you put the mu value. It's not the same thing. Mu is a ratio. It's a characteristic of the surfaces. Okay, so there's my givens and my free body diagram. Important things, okay? Important things when you're calculating the work done by an object. So we want to find the work done on the object by the student. On the object by the student. What's important? What's important? I'm going to highlight them if you tell me the correct answers here. What is important? I want the work done, again, by the object, by the student, on the object itself. Yeah.
FP and FN.
Yeah, FP is extreme. It didn't work well. FP is extremely important. Okay, we need to know what the student's force is. Why are you saying FN?
Is that right?
It's not, but why did you say it? I'm just curious. Because we're going to use it in a little bit, but not right now.
Wait, so we're trying to find the work done by the student on the desk?
Yep.
Because, I don't know, I just thought because they're putting the force of 12 and 20, I was like, I thought they were like.
Well, 20 is the table pushing back up on the weight, right?
Yeah, it's kind of like isn't that the weight of the desk?
It is.
So I thought like you would need the weight of the desk to incorporate the weight of the force.
Okay, well, believe it or not, ready? If I push this object with 1 Newton for 1 meter, and I push this object with 1 Newton for 1 meter, same amount of work is done on both objects. So the weight doesn't affect the amount of work done by the person on the object. Where will Fn or the weight come into play in this problem? Can anybody
Floor and
see the future?
desk.
Was it?
Floor and desk.
Yeah, why?
Because
Do you know why? Keep going, yeah, yeah.
I mean, because the friction, because it's pushing back.
Okay, it has to do with the friction, but more specifically, I want.
Why do you have to do?
Yeah, why is Fn going to be important later in the problem?
Because like between the floor and the desk, like FN and FG are acting on it. That's
It's a
what-
simpler answer. You guys are overthinking it.
Yeah.
It's simpler than that.
Obvious, normal force times the force constant is your friction force, which is
Your
force-
coefficient.
Yeah, your coefficient.
Force. Yeah, very good. Normal force times mu is what Ff is. Remember that? Ff equals mu times Fn. So later on, when we need the force of friction for part B, we're going to need to utilize Fn then, not right now.
So you need FG.
So right now, we need to know how much work is done by the student. So we need to know how much force the student applies, and for how far does the student apply that force.
Oh, I didn't even see. I didn't even.
Okay, the distance traveled there. So let's go ahead and look at this. So part A. Okay, there's our formula. What's the angle in this problem?
0,
Why?
because there is no angle.
Thank you, but give me more of a reason.
Because it doesn't say like the student is like pushing at an angle of whatever. It just says.
Horizontal.
Thank you, there it is. It says a student pushes with a horizontal force. If the force is horizontal and the object moves horizontal and they're both going in the same direction, the angle is 0. It's always going to be 0 if there's a horizontal force and it's moving in the same direction. It's going to be 0. Cosine of 0 is 1. That has no effect on the problem. The amount of work done is, yeah? 200 and?
88.
Good. Okay, 288 joules. That's the work done by the student on the object. Again, who can explain to us why is that work done positive? Why is that work done positive? Yeah?
He's pushing the object, giving it more energy.
You're giving the object energy. You're causing it to move to increase its energy level. Dragon Ball Z reference again. You like that? Energy level? No? So you get it? All right, a few of you guys maybe get it. So you're increasing the energy level. You're I don't want to say powering up. That's really just too corny. All right, so let's go to part B now. Part B says, find the work done by the floor on the desk. By the floor on the desk. If you want the work done by the floor, we're looking at the force of friction now. You go back up to the other one if you want. Put a little P right here as a subscript so you recognize that this was FP earlier in this problem, okay? Put a little P as a subscript because the pull was what the force was there. Now you're looking at the frictional force because the frictional force is what causes the floor to do work on the desk. Times the distance times the cosine of the angle. Now, friction is mu times Fn. Still, times the distance times the cosine of the angle. I'm literally applying formulas from last chapter. I'm saying friction is mu Fn. I'm doing that because I know mu and I know Fn. What is theta? No, come on. It's moving that way. Friction pushes that way. What's the angle? 180, always. That's what I told you in the last example, right? Whenever it's friction that's doing the work, the cosine is going to be 180. Or the angle is going to be 180, sorry. Normal force was 20 newtons. Distance traveled was 24 meters. Times the cosine of 180. What do we get? That was a big huff. Everything all right? This is so breathtaking, physics.
I got, it's not what I got.
Not -4,
Negative 96.
-96. You've probably forgot
Oh, I got 24.
something in there. Okay,
I didn't
yes.
multiply the distance.
Okay, -96 joules. Why is the negative amount work?
Because it's friction.
Friction does work on the object, but it causes the object's energy to decrease. What's the net work done? How do I figure it out?
I don't have the mental math.
Sum them together, 288 plus -96. What is it? 192. And my units are joules again. Okay, joules. So we literally just sum those two things together. Now, an alternate way to figure out the net work done, you could have found the net force originally. What was the force of the person pushing? Well, look at your notes, please. What was the force of the person pushing? 12. Anybody know what the frictional force was? What do you get when you do mu times Fn? What's 12 minus 4?
8.
Bear with me. 8, right? 8 times 24 is 192. So if you want to find the net work done, you can write this down. If you want to find the net work done, you could find the net force first. And I'll show you that. You could sum them together like we did, that works, or you could do this. Now there's no need for the angle now because we're incorporating the angle when we find the net work or the net force. The force you're pushing with is 12. Friction pulls back with -4 newtons of force times a distance of 24 meters. That will also give you 192 joules. Okay, the cosine 180 is already taken into account because this sign is negative because friction is negative. So 12 is your pull. This is FP minus FF. That's the net work done. So you could approach it that way as well. Either way you would like to is fine. Okay? Your homework tonight is on the next slide. Yeah. Yep. Homework due tomorrow, normal. Office hours after this, please.